Welcome back, my friends. This is William M. Briggs. This is episode, what are we up to? 46 of Uncertainty and Probability Theory, the Logic of Science. We're still on cause. We're going to be on cause this week, and we're going to be on cause next week. And then finally, we're going to move into models. We're going to move into scientific models and understand models in all their glory. I know a lot of people are anxious to get there because they want to see how the math works to create these models and the strengths and weaknesses of all these models and so forth. But we need to understand the philosophy of them thoroughly before we go and start using these models in a wanton fashion, at which point we're going to start interpreting their output in all the wrong ways. Even if we're going to have, in the end, we're going to have spent 47 weeks. 47 weeks. I think I threw in a couple of extra classes on top of this, which I didn't number. So 49 weeks, almost an entire year, explaining all of this philosophy of how to interpret all these things, which most of us, I guarantee, will have forgotten the minute we start spitting the output of these models and examining them and so forth. Well, today, explanation. Well, that's another word for cause. Aristotle's four causes, the formal cause, the material cause, the efficient cause, the final cause. This is another way of saying explanation. This explains why something is the way it is. So explanation and cause are, or should be, synonyms. They're the same words, but in English there's some subtleties of difference and so forth. And so we have this idea, it's called inference to the best explanation, or abductive reasoning, but I call it here abduction for a little pun I'm going to make. Abductive reasoning is called inference to the best explanation, and there's a lot of weaknesses with this, and I want to describe them to you and to show you that really it's all just trying to find the cause, trying to find the explanation of something in the first place, and that's limited by your experience. And there's no magic trick. Abductive reasoning is not going to bring you any closer to finding out the truth of something than any other way of looking at things. It's unfortunate that it's somehow separated out, but it is, and it's often given by how surprising certain data is. And they'll say, here's an observation about the world. We're going to come to an example I'll give you here. Oh, that's surprising. Based on what? You can only have something that's a surprise. The probability and surprise is quantified by probability, but we know that all probability is conditional, so it has to be conditional on something. What? That's what we're going to look at here. So let's look at an example here. So we always choose the proposition of interest. The proposition of interest is always up to us. The thing about the world we want to explain is something we pick. All right? So we're going to pick, your dad comes in the house. This is going to be our data. Dad comes into the house and has red paint on his clothes. I use this from something that triggered my memory when I wrote the book. I can't remember what it was at the time, but I was remembering my dad in this. He comes back and he's in the house with red paint on his clothes. Well, what are some possible explanations? E. He was painting the house. He was painting a chair in the garage. What else do I have here? He was painting the car. Some aliens abducted him, and these are probe marks. And it's clear, I hope by this, that I can go on forever. I can go on listing explanations, and there are going to be an infinite number of explanations that I could bring, and that's what we're going to concentrate on next week, formal proof of that, to explain this data, to explain this observation. But abductive reasoning, if you look at all the textbooks and everything, it's supposed to bring us to the best one of these. It doesn't work that way. It just doesn't work that way. It does in the sense that it's our reasoning from our past experience and so forth that brings us to an explanation that we accept. Whether or not it's true depends, as we'll see. Okay, but we have all these kind of things right here. So, for instance, suppose, though, I'm not considering any of these. I didn't think of any of these. I'm limited in my thought, and the only explanation I have is the house. I see my dad walk in the door, and I want to explain that. He's got paint on his clothes, so I'd say he was painting the house. So what's the probability of, let's look at this thing carefully here. What's the probability of the explanation given the data? Well, some people will try to write Bayes' theorem like this. They'll try to write it, they will write it like so. They'll say the probability of the data is there, and the probability, the so-called prior probability, and the probability of the data itself. This is always an error. Remember, this is like episode, boy, I can't even remember, 5, 4. You have to go way back. You can look at the class page. It's linked down below. You have all those links. You can go and find it. But this is one of the first things we did. This is always an error because there is no such thing as the probability of the data. You can, some people say, oh, yes, there is. I can write the probability of data like this. It's just a sum over, whoops, the probability of the data given explanation I times the probability of explanation I. For all over these I explanations that we have. Well, here we only have one explanation. We have Dad's painting the house. There is no unconditional probability. There is no probability this explanation is true. I picked it. The probability, therefore, based on my picking it, is 1. And the probability of the data being explained by it, therefore, must be 1. And the probability of the explanation being true given the data we've seen must be 1. So probability theory here is of no help to us. If this is the only thing I'm going to bring to the table and say this is the explanation, then inference to the best explanation gives us the one we started with. It's as simple as that. So let me try to see if I can hone in on that for you. If you have any doubts at all, again, you know, this is the only explanation we brought, so the probability of this has to be 1. And we've only said we've had 1. The probability given the paint clothes, the probability that explanation has to be true has to be 1. And 1 has to equal 1. So these two terms have to equal 1. The probability of the explanation of data is 1. The probability of seeing the data is 1. So everything is equal to 1. This incorrect way of writing things doesn't help us. So let's write Bayes' theorem correctly. And how we think of these things, and let's incorporate our experience. And how did I come to this house idea in the first place? Well, I searched my experience. Yours will be different, and I came to that. So we have to write all of the information we have, and of course we could write it in shorthand notation. But remember, there's all kind of information that's in probability equations that's often not shown. Absolutely always there, but almost never shown, and you remember this, is the definition of the words and the terms used. The meaning of these things, all of these symbols that we're writing up, the absolute definition are in there. And sometimes definitions can be hazy and different, and they vary according to people and so forth. You know, not everybody has the same, holds the same meaning of words that they hear and use. That one we all learn by hard experience. So, okay, so let's let this be, let's let the probability of the data be small, of this particular data with these two, that's all I have, the paint on the clothes and the house, but not 0. Well, yet if all we have, this is true, we say that the probability of this data being true on this explanation is small. But since the only thing we have is the explanation, it still must be the probability of explanation given the data equals 1. Because we have no other explanation. And if it is, here we'll harken back to last week, if we say it's impossible, now we run into these, we think about these things, this is what I've observed, but the only explanation I can think of is impossible. He couldn't have been painting because you know, he doesn't know how to use a paintbrush or something. I should come up with a better explanation. But you've run into all kinds of situations in life, and I should have thought of these beforehand. But we see something, some data that we need to explain, and we want to explain, and the only explanation we can come up with makes it impossible. So we say, this is just not possible. You know, he comes back with paint on his clothes, but there was no way he could have been painting because he just came in from work. But the only thing I knew he was going to do is paint the house. So this is impossible. Then it must be the probability of this explanation is 0. That works. That works. Okay? But this is falsification. Well, we did falsification last week. We have a theory that said it's exactly precisely 0. We've seen it. Therefore, the explanation must be, the hypothesis must be, the theory must be, the model must be false. Okay, so we have a case where we've, from abductive reasoning, brought, the abduction. The abduction was, did I make my pun? You know, the aliens abducted him, the red marks, I'm assuming it was red, are probe marks on his clothes. Okay, that's hilarious. You could laugh down in the comments below. Okay, so let's write Bayes' theorem correctly, given our experience, and we'll see how strong or weak abductive inference really is. Okay, so we're after the probability of our explanation given the data and whatever experience. I'll just write EXP for experience. I don't want to, in the book, you see down below, there's a link to the my sites, wmbriggs.com or wmbriggs.substack.com, where I'll have an excerpt from chapter 7 of Uncertainty. It spells all this out so you don't have to get confused if you do, if you're just seeing this video. Okay, so let's write this. The probability of E given the experience times the probability of data given experience. And this we can break out, remember, we can break out if we wanted to. We don't have to do it here, but I'll just write out one term of it and you'll remember the rest. Experience E1 times the probability E1 given experience plus the other one. E, not E1, not E. In this case, it would be not E. Well, I'll write it out now because I started it, and if I don't continue it, someone will say, what did I do? D given EXP given, I'll say E contrary times the probability of E contrary given experience. Okay, we can bust that denominator out like that. That's just the total probability. We did that on episode 4 or 5 or something like this. This is Bayes' theorem written properly. Now we can say, well, how did we come to this explanation? Well, we came to this explanation. That's the only explanation I had. So the probability of this explanation, given the experience that I brought, whatever term you want to use for it, doesn't have to be experience. I'm writing experience because it's a shorthand, but my memory, the reasoning faculties that I have, all the other premises that I have milling around in my brain, there we are, and I came up with this explanation of house. So that probability has to be 1. And this probability in the end has to be 1 again, because I've considered no other explanations. But here at least we've written Bayes' theorem properly. But what if we came up with other explanations? I'm not going to say the house, and then I can also consider garage. He's painting say a chair in the garage, something like this. And I'll call this one E1, and I'll call this one E2. Now, let me give myself some extra space up here. That's up to me. My experience gives these to me. Now, here's the trick. Here's where you have to be very careful and where more mistakes are made than anything else. This will happen in models all the time, absolutely all the time. My experience says, or the reasoning powers or the history, whatever it is that's bringing these things to mind. That's the problem with abductive reasoning. It relies on your memory. It relies on your reasoning power. It relies on all these things. And there's no way it's going to give you something that isn't there. And if the real explanation isn't there, you're not going to get there. All right? It's just impossible. So basically, what abductive reasoning is nothing more than a memory check, nothing more than a reasoning check. That's what we're going to see. Okay, my experience says it must be E1 or E2, and has to be 1. Has to be 1 of these, and none other. That's what my experience told me. If that's the case, if that's what my experience told me, it could only, and nothing else, and nothing else, and nothing else except for the tacit premises Oh, by the way, speaking of tacit premises, one of the premises for the house thing, there was a tacit premise in there I let slide, and you guys should have caught me on this, is that I said the house was the only premise we were considering and the paint on clothes. There had to be a tacit premise in there that when one paints a house, one can get paint on clothes. That's a tacit premise. It's the whole thing of the explanation. It's that tacit causal explanation that we brought to the model, that if we are not careful in our shorthand notation here, disappeared. And then we somehow think the model, in the end, when we get out the result that the probability of house is 1, that it somehow told us the cause. No, that premise was always there. We brought that premise to the model, but it was tacit. We didn't write it out. But it's there. It's always there. We need to be very careful. But here I want to say, and that tacit premise is also here, that either of these activities will put paint on clothes. That's a causal explanation right there. Here's the real key, though. If all I'm bringing, it has to be house or garage. Has to be one of these. And the tacit premise that either one of these can put paint on clothes. And nothing else. This is logic now. Nothing else. That doesn't mean later you can come on and stick on extra premises that weren't there. This happens all the time. The model is written as it is, and people will interpret it by thinking that there was all kind of other premises that were in this model that weren't there, or that should have been there. And they'll say the model was wrong because these other premises should have been there and they weren't. That's not how it works. We take all logical statements, all logic, and probability is just the extension, the completion of logic. We just take them as given. We interpret them as they are presented to us. All right? That's how we have to take all of these things. There's no other way. So if this is the case, then it must be the probability of E1 or E2 given experience must equal 1, and therefore the probability of E1 given experience plus the probability of E2 given experience must equal 1. And therefore it must be that the probability of, here's where people start to quail, equals the probability of E2 given experience. We know these are the only ones we brought, and we had nothing else. Therefore, one of these explanations must be the correct one. We said so. We said so. Therefore, the probability of either one, since they're independent of each other, and I don't mean that in the statistical sense, we're going to come to that word later, and I don't like it. I'd never use it in that sense, except to show you why I don't like it. But in any case, this is a true equation. As you can see, the probability of one plus the probability of the other has to equal 1. And therefore, they must be equal, because I have nothing else in these two, in this knowledge that I have right here, to decide between the two. There's nothing else in this evidence that I have in my experience that allows me to differentiate between house and garage. That's what I brought to it. There's nothing else there. There's no other information that is there. I could put other information in, and then the problem changes. But let's not. Let's see how we get along with this kind of a thing. All right. Well, given that's the case, let's look at this. We could just make this a 1 everywhere. I'll make this a 1 because it doesn't make any difference. A 1. A 1. Okay. So now I want to know the posterior. Remember these terms? This is our prior, based on our experience, and here is our posterior probability. We want to know what the probability of this explanation, 1, house, is, given the data we've observed, paint on clothes, and the experience that we brought to this. That's all the information we say we have. That's all the information we say we have. Nothing else is in there. Nothing else. I stress this, and right now it may even seem absolutely trivial that I am stressing this. Why is he going on and on about this? But you're going to see when we start going through these models how quickly this flees from your mind. And it happens all the time, and you won't believe it, but it does. Okay. Now, what's the probability of this? Well, a half. We did that already. This right here, the probability of experience is E1 or E. So this right here, just the numerator here, probability of B given E1 and E1 or E2 is equivalent to, well, the probability of it's either E1 and it's E1 or E2 is equivalent. Either one of these are explanations, and this is an explanation. This probability must be 1. These are explanations, after all. These explain why the data is the way it is. So if E1's an explanation, the probability of that data must equal 1. Okay. Now, the probability down here, the probability, we could bust it out. You can do it like this, where the E contrary becomes E2 in this case. You could do it this way or this way. I'll leave it as homework for you to do it this way. But we have an explanation here. We have experience gives us one explanation or another. And both explanations explain the data. E1 explains the data perfectly. E2 explains the data perfectly. So this probability must be equal 1. And so this probability over here equals a half. 1 times a half divided by 1 is a half. The data doesn't tell us anything more because, and here's the big drum roll secret, this data gave us what the experience was in the first place. Abductive reasoning is nothing but thinking of possible explanations that you could that are consonant with the observed data that you have, and that's it. I could have weighted these differently and said, well, I think this one has the probability of the garage. I think that's less likely. Okay, so that's less likely, and the house is more likely. You're done. All right? You have done nothing more than search your memory or search your reasoning powers on your memory, or however you want to put this. That's abductive reasoning is nothing more than a memory search, and that's it. You don't gain anything by going through this mathematical formula. That's the whole point. You started with this because the data was the thing that informed your experience in the first place. That's it. That's the big secret. There is no secret. So there's not, when you see all these inference to the best explanations, and this explains philosophically how we really do it in science, it doesn't work like that. Because if you don't know anything about it, if, for instance, what are these cargo cults that had, you remember cargo cults, I guess it was in World War II. Somebody can correct me. My memory's shady about these. See, my memory is shady about these things. Some planes had dropped off on some remote Pacific island a bunch of cargo. And after the war, the cargo stopped coming, so they built bamboo or something, simulacra of airplanes, hoping that therefore would bring cargo. That was the explanation for the cargo, for them. That's all they came to. They never came to the explanation that the planes had to be flown and all that kind of stuff. So they used abduction. They used abductive reasoning to the best explanation. That's the best explanation they could come up with. So they were, according to the textbooks, reasoning in a proper way, in the proper Bayesian abductive reasoning way. But they came to the wrong answer because they could not even fathom the proper answer. And how do we fathom proper answers when our experience? So we might have all of these things here. I might have a whole list of these things, including the alien probe and all that kind of stuff. And none of them turn out to be right in the end. My dad reveals that he was in a lunch hour at break. He and his buddies went to one of these, what do you call them? Those paintball places or something like this and had a war. That's it. I never even considered, never even thought about it. Therefore, I never came to the best explanation. I never came to the proper explanation because it wasn't available to me as an explanation. How do we come to these things? How do we generate new knowledge? How do we come to find answers when there is no explanation? Well, that's back to intuition again, back to induction again. Induction, intellection, induction by analogy, induction reasoning, all these different forms of induction that we had. That's all. We went right back to the beginning, and that's where we are. We've never left any of that stuff. That's why I stressed it so much. That's why I'm stressing it again now. So there is no abductive reasoning. There just isn't there. It's just testing your memory. But if you're in your reasoning powers, but if it isn't in there, the real explanation isn't in there, you can't get it. you can't get to it. Just because it's not in there in the first place. And none of these probability equations do a darn thing for you. You always end up right back where you started. Now, I hope you really see this because there's a lot of stuff written on this and it's just wrong. It's just not right. It's just trying to paint a picture of how thought works that isn't correct. So next week, finally, our last real, we're going to emphasize cause from now. Every lecture this class lasts, but we have to understand something called it's called overdetermination. I don't like the term. It always seems to me it should be underdetermination. The idea is that we have a set of observations and there may be any number of theories that fit that data. All right? And when we're satisfied we have the correct explanation, in science this happens all the time. I have the best theory that explains this data. Someone comes along with a better one, because any set of data it's going to turn out, any set of data observations we have is consonant with, I like the word consonant, is consonant with an infinite number of theories and models. And I'm going to give you some brain teaser examples and all that kind of stuff. So that'll be some fun. And you know, there's no, that's the whole point. We're always having to rely on faith in some way or another in our inductive powers, and there's no getting around it. There's just absolutely no getting around it. Not in science, not anywhere else. Okay, that's it for now. Down below, wmbriggs.com, wmbriggs.substack.com, and you could, oh, and I'm supposed to, I was told, please subscribe. If you do, you're at YouTube. If you're at Substack or the blog, one of these places that the video shows up, please subscribe. I know you know this, but I was told they know it, but they should be reminded. So okay, I'm reminding you, please subscribe and all that kind of a thing. Thank you very much for watching, and I'll try to get to any questions that you have on the blog. That's it for now.